Hi, my name is Hakim. I'm a student of SCI6001. My area of study is Master of Science, major in Mathematics and Statistics. But my research topic is the analysis of Navier-Stokes equations in terms of vector calculus and complex analysis. My supervisor name is Dr. Navin Raj. First of all, I acknowledge the traditional custodians of the Daruk community where I live in the Canterbury-Bankstown area. The Daruk people are the traditional owners of this land, and I pay my respect to the elders past and present of Aboriginal people. It always was and will be the Aboriginal land. So, introduction. Fluids are an important part of our daily lives. We are familiar with water, air, blood, and many other fluids, each playing a vital role in our health and environment. We know that blood flow plays a crucial role in identifying conditions such as heart attacks, strokes, hypertension, and other cardiovascular diseases. Accurately monitoring and controlling blood flow helps doctors and specialists make life-saving decisions during diagnosis and surgery. The dynamics of fluid, such as blood, can be described by one of the most important partial differential equations in advanced mathematics named as Navier-Stokes equations. These equations are used to model the flow of incompressible fluid. The properties of fluid, velocity, pressure, temperature, viscosity, gradients, force interactions are successfully shown by these equations. Vector calculus represents fluid dynamics by describing vector fields, gradients, divergence, curl, and surface integrals related to fluid flow. Whereas the complex analysis is another part of mathematics that offer tools for investigating the behavior of the functions relevant to fluid dynamics. Although many studies use the Navier-Stokes equations to model fluid properties, but few explore them using the combination of vector calculus and complex analysis in details. Hence, we need to explore the Navier-Stokes equations through the analytical frameworks to improve the efficiency of fluid flow and its monitoring tool. So, aim of the research is to analyze the Navier-Stokes equations to better understand fluid dynamics in three-dimensional space. Vector calculus tools such as surface integrals, divergence, Curl theorems, Green's and Stokes theorems can describe fluid motion and help us to interpret phenomena like turbulence circulation of fluid as per Haas 2025. And whereas complex analysis tools will contribute us by tracing singularities and evaluating residuals and improving the precision of fluid modeling as per Potash et al. So we can derive the key question from the research: which vector calculus tools best interpret the Navier-Stokes framework? How can complex analysis reveal fluid behavior in relation to these equations? Can combining both approaches uncover new patterns in fluid flow? What limitations exist in current methods and how can they be addressed? By combining this mathematical approach, this research aims to improve fluid modeling accuracy and support future research in fields such as oceanography, engineering, and medical sciences. So background informations, the Navier equations include dependent and independent variables as shown by the following equations as per Olvar 2014. Here the dependent variables are u, v, w, p, while the independent variables are t, x, y, z. The variable t denotes time, x, y, z correspond to the spatial coordinates in three-dimensional space, whereas the u, v, w represent the components of the fluid's velocity vector. P denotes the fluid pressure. The symbol v on the right-hand side of the first three equations is the fluid's viscosity as per Olvar 2014. Now we can review some literature. The author Michael Corral states that vector calculus examines the functions involving two or more variables within three-dimensional spaces known as vector field. The author Chen states that analysis of surface and gradients can be conducted using Euclidean geometry, which is inherently tied to these spatial dimensions. However, neither Michael Corral nor Chen and Lang offer a direct comparative analysis between the Navier-Stokes equations and the geometric structure of Euclidean space. Tyson and Fries use vector calculus to model fluid flow on curved surfaces by reformulating the Navier-Stokes equations for finite element analysis. Their study does not offer a detailed component-wise breakdown of the Navier-Stokes equations from a vector calculus perspective. Schmidt and Didlaukis use conservation laws and Gauss law with finite differences method to solve incompressible Navier equations. However, the study does not include key vector calculus concepts like Green's theorem, Stokes theorem, etc. Galdi presents a formulation of steady-state Navier equations using gradient and Laplacian operators to model viscous fluid flow, but it does not address Carl Green's theorem and Stokes theorems. Now we examine from the complex analysis. Mazun and Mohabbi studied harmonic function in fluids using Navier equations and a spring mass system. The study highlights the role of harmonic function that central to complex analysis in simplifying fluid flow problems. However, the above studies overlook other fundamental elements of complex analysis such as Cauchy-Riemann equations. Akishev proves the existence of smooth, unique solutions to Navier equations using harmonic energy Laplace equations and Fourier transforms. This study needs a high-level understanding of complex analysis. Shorten uses homotopy analysis with Taylor series and Fourier transforms to solve three-dimensional fluid flow equations and study solutions behavior. However, this study does not discuss about another important topic like the residual theorem of complex analysis. The reviewed literature lacks a comprehensive examination of Navier equations through the combined lenses of vector calculus and complex analysis. So we can use the following tools for this research. As an example, for vector calculus, line integrals will be used to integrate multivariable functions or vector fields along curved of Navier equations. Surface integrals and flux will measure flow across surfaces in 3D. Curl function will capture local rotation of or swirling of fluid. Divergence theorem will help us to convert surface integrals of flux into volume integrals. Green's theorems will help us in fluid flow analysis by turning line integral around a closed curve to a double integral over the region it encloses. Stokes theorems will help us to interpret the simplified Navier equations in terms of circulation and swirling of fluid. And complex analysis, Cauchy-Riemann equations will help us to analyze the smoothness of fluid flow. Harmonic function will help us to model fluid potential using Laplace equations. Taylor series will help us to approximate flow variables. Singularities and Lorentz series will help us to analyze breakdown near critical points. Residue theorem will help us to analyze behavior of the function near singularities. Fourier transform will help us to analyze the Navier equations by converting complex fluid motion into simpler frequency as per Orloff and Strange and Harman. Now, how will perform this research? First of all, we'll review the existing literature and find the gaps. Then apply both techniques. We use conformal mapping, compare fluid simulations with prior studies. It will take around 12 weeks times. Resources will be used: LaTeX, MATLAB, Python, EndNote, cloud tools for writing, computation, referencing, and data management. Now, outcome from the research. This research adopts a dual framework approach, vector calculus and complex analysis, to enhance the understanding of Navier equations. Vector calculus tools such as surface integrals, curl, divergence, Green's theorems, Stokes theorems will help us to interpret fluid motions, turbulence, and pressure variations. Complex analysis tools including singularities and residue theorem will help us to offer deeper insights into fluid behavior and modeling. Together, this method will address key mathematical challenges in incompressible fluid systems and propose simplified solutions. This finding will have practical relevance in aerospace and engineering and medical sciences, particularly in improving blood flow models for cardiovascular diagnostic and treatment. So finally conclude, this research will address a critical gap in the mathematical analysis of the Navier equations by integrating two powerful frameworks, vector calculus and complex analysis. While many studies model fluid flow using these equations, few explore their full potential through the combined application of surface integrals, divergence theorem, Carl theorems, Green's theorems, Stokes theorems of vector calculus alongside the tools of complex analysis such as singularities, harmonic functions, residue theorem, and so on. By adopting this dual framework approach, this study aims to deepen our understanding of fluid dynamics, particularly in incompressible systems, by revealing patterns in turbulence, pressure variations, and flow behavior. This methodology not only enhances the precision of fluid modeling but also supports practical advancements in fields such as aerospace engineering and medical sciences. Ultimately, this research contributes a novel analytic perspective that bridges theoretical mathematics with real-world fluid dynamics challenges, offering a foundation for future interdisciplinary innovations. Thank you. Here is the reference list.